morning and welcome to lecture 51. In the last lecture, we have been covering some of the topics pertaining to multi-user detection in CDMA. So, we would like to begin today's lecture with a quick review of lecture 50, where we have been talking about the multi-user detection in CDMA, and in today's lecture we will introduce a new form of receiver, a suboptimal receiver, but one that performs very well in the context of multi-user environments. That is called the minimum mean squared error receiver, or MMSE receiver, for multi-user environments, and this will be built on the well-known principle of orthogonality in optimal filtering theory. So, we would like to incorporate that in the context of an example, and with that we will complete our discussion of the introduction to CDMA. The next unit that we will be covering will be the topic on multiple antennas at the receiver, multiple antennas at the transmitter. So, that would be referred to as a multiple input, multiple output, or a MIMO system. So, we move from the CDMA context into the multiple antenna environment, and that will be the next the latter half of today's lecture. So, a quick summary of the multi-user detection that we have been discussing so far. So, the problem of multi-user detection, if you were to think of it as a family of solutions, the first solution that we referred to was the optimal or the maximum likelihood receiver, where we computed through exhaustive search what was the vector that was transmitted by each of the k users. So, our assumptions are that there are upper k synchronous users, each of them transmitting a binary bit B1 through Bk, and our goal is to estimate the vector B1 through Bk at every instant of time. That would be our multi-user detection problem statement, and we saw that the optimal solution would be the maximum likelihood solution, and it is a solution that turns out to be computationally intensive. It is exponential in complexity in terms of the number of users that are present in the system, and also depends on complexity increases with the size of the constellation that you are transmitting. So, this would be a receiver that we would like to use, but is complex. On the other hand, we have also looked at suboptimal receivers. So, in the last lecture we introduced a very useful solution, one that is widely used, that is the decorrelating receiver. So, this we showed is a receiver that has lower complexity, but at the same time achieves good performance. It has some limitations which we talked about yesterday, and we will also continue to discuss it today. What we would like to do is present another suboptimal solution, but one that performs even better than a decorrelating receiver without a significant increase in complexity. So, that is a second suboptimal receiver, but one that performs close to. The MMSE is also referred to as a Wiener filter or a Wiener filter based solution. We will refer to it as the MMSE solution. So, in a nutshell, the optimal ML receiver that we have talked about in the earlier lecture optimizes the probability, maximizes the probability that we have transmitted a vector B hat and the received signal R of t. Now, R of t is a continuous waveform. So, we are maximizing the probability that the received vector is R of t when the vector B hat was transmitted. So, in other words, given R of t, we are trying to find that vector B hat that maximizes this probability. So, using a series of expressions and steps, we have shown that this B hat is nothing but the vector B that maximizes this expression. And this is the computation that we need to do for a maximum likelihood receiver, and this is the basis of the formulation that we have shown. Okay, so this is the expression we have to try all combinations of the vector b. So therefore, the number of combinations would grow exponentially as the size of the vector grows or as the size of the constellation grows. So this is the maximum likelihood receiver metric, and we would optimize it over all possible b1s and choose the one that gives us the best solution. So this was the optimal receiver or the maximum likelihood receiver. Now on the other hand, the decorrelating receiver was formulated differently. So if the received vector, not the received continuous time waveform, but this is the vector of outputs, this is the outputs of the k correlators, and if you write down the expression for that, the output of the k correlators comes out to be R, which is the correlation matrix which takes into account the correlation between the different spreading waveforms, the vector of bits transmitted by each of the k users plus eta, the noise component that is present in the measurement of each of the antennas. So if this is our underlying equation, then we showed that the decorrelating receiver computation is the following. It says that what we have as the best estimate of the transmitted vector is nothing but R inverse times the output of the k correlators. So that would be our expression for the decorrelating receiver, and again this was something that we spent time deriving. Now just as at the close of the last lecture, we mentioned that it is good for us to understand why a decorrelating receiver works and what are the underlying mechanism. So if you were to write down the expression just for a 2 by 2 case, so it is easy for us to visualize, we see that the R matrix can be written in terms of the correlation between the two spreading waveforms. We call it as rho. R inverse, we can write down the expression, and we write down the expressions for the output of the correlators. Each of the correlators will produce the following expressions, and R inverse times R gives us the expression. So this is the expression that we saw in the last lecture. This is where we saw that the decorrelating receiver completely separates the two users, and therefore we do not have any issues with the near far problem or the interference from one user signal leaking and affecting the decision of the other users. So we see that there is a clean separation of the two. We did make an observation that there is a potential for noise enhancement because of the way the decorrelating receiver works. We have in the noise term 1 minus rho squared in the denominator. Rho is a number that is less than 1, so therefore the denominator will become smaller, and therefore the noise variance is likely to increase. Another very interesting way to visualize why or how the decorrelating receiver works is to relook at the expression, and this is what we mentioned towards the end of the last lecture. Now if you were to think of the received signal R of t, now normally you would multiply it with G1 star of t, and you would then follow it up with the integrator. Now instead of that, if you multiplied it with G prime star of t, where G prime star of t is an expression that is given in the following manner: G1 of t minus rho times G2 of t into 1 minus rho squared. If you think of this as a modified despreading waveform, and then you apply it in this form, R of t multiplied by G1 prime star of t followed by the integrator, you would find that the expression that we obtain is exactly the expression that we got for R inverse R. So in other words, the multiplication by the inverse of the correlation matrix, the correlation of the spreading waveforms, can be equivalently represented as a modified despreading sequence which takes into account the correlation between the spreading users. Again, this is an interesting interpretation that helps us understand how a decorrelating receiver works. So the R1 prime of t, which is what you would obtain by using this expression, by using the r of t multiplied by g1 prime star of t followed by the integrator. If you write down the expressions, you would get the expressions given on this graph in this page, which is exactly the expressions that we got for when we multiplied by r inverse r. So this set of equations is identically equal to what we got by multiplying r inverse times r. Okay. So both are equivalent. One is multiplying by a matrix inverse, the inverse of the correlation matrix. The other one is doing the receiver using a modified spreading sequence, and both of them give us an interesting perspective. So we have looked at the following example. I would like us to quickly look at it once more. It is a 2-user synchronous CDMA. At the receiver, the values of the output of the first correlator and the second correlator are given by minus 0.08 and minus 0.47. Now, given that this is a binary decision, whether you want to declare it as a +1 or a -1 with the threshold being at 0, both of these would map to -1 because both of them have a value that is negative. We are given that the correlation matrix is 1, 0.33, 0.33 and 1, and using this information we first of all estimate the maximum likelihood solution. Maximum likelihood requires us to try all combinations. All combinations would be 4 possible combinations of the transmitted vector. For each of those we have computed the metric B Hermitian R plus R Hermitian B minus B Hermitian RB, and with that we are looking at the following different values of the metric, find out which is the maximum. All of these are negative numbers, so the maximum would be the least, the one with the maximum of these numbers is minus 0.56, and that corresponds to the second vector 1 comma minus 1. So this was what we obtained as the vector. Now, if for the same problem, if we had done the following, we had done the decorrelating receiver, which is R inverse times R. So this would be the same as R inverse times the matrix, the vector that we have received, minus 0.08 minus 0.47. Please do compute the R inverse matrix, and you can find out that this corresponds to the following expression. R inverse R comes out to be 0.084, and this one corresponds to minus 0.498. And if you were to quantize this information into plus and minus 1, this would lead to the following quantization. The first bit would be, since it is positive, would be mapped to a +1, then the second bit would be to a -1, and we find that this is the same as the solution that the maximum likelihood receiver also obtained. And this is different from what you would have obtained had you applied the quantization directly to the output of the correlators. So there you would have made a mistake. It would have been -1 comma -1, whereas the correct answer is -1 +1 comma -1, which is consistent with the result obtained in the maximum likelihood case and also with the decorrelating case. Okay, so with this as the basis, we would now like to move into the next section, where we would like to understand and implement the performance of a MMSC receiver, and this is the starting point for the second suboptimal receiver that we would like to study in today's lecture, and this is the formulation. Okay, so the decorrelating receiver, so just for reference, the decorrelating receiver does the following computation. Decorrelating receiver does the following computation, which says we are given the expression that the output of the correlators is R times B plus eta, and the decision vector B hat is given by R inverse times R. That is the expression for a decorrelation receiver. And of course, if you were to substitute for R, this would be R inverse times R times B plus eta, and expanding upon this equation, this would give us B plus R inverse times eta. And what we find is that the decorrelating receiver is focused on obtaining an expression for the transmitted vector, while it does not pay much attention to what happens to the noise, and this is where there could be a potential for noise enhancement. So, there is a potential for noise enhancement in a decorrelating receiver, which is something that we have mentioned multiple times because of its importance, potential for noise enhancement. Now, how would you formulate another receiver which takes into account the noise enhancement? And this is where we would like to present the MMSE receiver. Now, we make the assumption that in an MMSE receiver, that our best solution B hat is the vector of outputs of the k correlators multiplied by a linear transformation, basically a linear transformation of those vectors, which is denoted by a constant matrix A. So, if you were to assume that the outputs are obtained as some linear operation on the output of the correlators, k correlators, that would be given by B hat is equal to A times R, and this would be our expression for the linear representation in terms of the the bits transmitted with respect to the output of the correlation. So, the MMSE criterion says that we would like to minimize the error, and what is the error that we are trying to minimize? What the vector that was transmitted and the vector that was estimated, and we would like to minimize the square of this with the expectation in front. Okay. So, the metric that we are looking at is given by the expected value of B minus B hat, and B minus B hat is nothing but B minus A times R. B times where B hat we have represented as A times R, that is our expression for the output of the MMSE detector. So, this Hermitian times B minus AR. So, the MMSE formulation is can be stated in the following way very simply. We would like to find an expression for B which is a linear combination of the output of the k correlators. So, that is assumption step 1. The second one where we find the optimum B hat is by finding the B hat that minimizes the mean squared error between the transmitted vector and the vector that was at the obtained as the decision. So, the metric can be written in the following form, where it is a expected value of the magnitude squared, which is given by B minus AR Hermitian B minus AR. Now, one of the very powerful results in optimal filtering theory is something known as the principle of orthogonality. And what we would like to do is give a intuitive explanation for principle of orthogonality and use that in our derivation of the MMSE receiver. So, here is a quick overview of the principle of orthogonality. So, the principle of orthogonality says the following, it is a geometric interpretation. So, think of a 3-dimensional plane x, y, z, x in the horizontal direction, y and z, and a point A that is in the 3-dimensional space. Okay, it is in the 3-dimensional space and it has got coordinates in x, y and z. Now, here is the principle of orthogonality. Now, I would like to find an approximation to A but an approximation that lies in the xy plane. Okay. So, xy plane. So, if you were to think of it as in the following manner, that the approximation a hat will be alpha times the unit vector in the x direction ux plus beta times the unit vector in the y direction. Okay. So, if these are my unit vectors, alpha and beta are scalars. So, basically I am trying to find a approximation to this 3-dimensional vector, but in a 2-dimensional space. So, the question that arises is, which would be the best possible approximation to A in the 2-dimensional space? In the 2-dimensional space I have represented it as A hat. So, most students of geometry would immediately point out that the point of closest approach, which would be the error between the vector that we are trying to approximate and our approximation, would be that which lies perpendicularly below it in the xy plane. So, basically if you were to drop a perpendicular from the from A to the xy plane and you take its coordinates, that would turn out to be the best approximation to that. So, basically this point would become your alpha, this would become your beta, and then you would get the best possible approximation. I hope you are comfortable with the explanation. A is a point in 3-dimensional space. I am trying to approximate it in the 2-dimensional space in the xy plane, and I find that the point that is perpendicularly below it is the one that gives me the best approximation. So, if you were now to think of the error between the original vector and the approximation in the xy plane and call it as E, the vector E. So, basically A minus A hat is the vector E, or in other words A hat plus E would be equal to A, which is the equation that is given here. Now, given this expression, given the geometric interpretation, it is easy for us to see the following result, and this is a very key observation. We find that the vector E is perpendicular to the vector A hat, because it is perpendicular to the plane, because A hat is perpendicularly below A in the xy plane. Now, this is also means that you will be perpendicular to the components of A. So, ux and uy are the components of the unit vector, and the error has to be orthogonal to the components of A hat. In other words, the error vector is orthogonal to the plane that is represented by A hat. So, this is what we refer to as the principle of orthogonality. The best possible approximation A hat is that which produces an error which is orthogonal to A hat. The error must be orthogonal to the input vector which is the approximation to the given vector. So, given this understanding of the principle of orthogonality, I would like to go back and rewrite the principle of orthogonality. We are trying to find that solution that minimizes the mean squared error, and from the principle of orthogonality we also know the following. The principle of orthogonality states that the error must be orthogonal to the vector. So, the expected value of the error B minus AR, this is the error, and this will be orthogonal to the input vector R. So, the orthogonality condition is given by error orthogonal to R, and where R is you can think of R as the components of the best approximation, and AR being the best approximation of the received vector. So, this is the principle of orthogonality, and this must be equal to a 0 vector. So, this is a principle. So, the minimization of the squared error can be translated or simplified as a condition which is given by the principle of orthogonality. So now that we have this form, we would now like to simplify it and see what is the result that we obtain from this expression. So the expansion of this expression would be expected value of B times R Hermitian minus A times R Hermitian. This has to be equal to 0. Now, what we would like to do is simplify it further and derive a expression for the results that will be helpful for us. So, we call this as equation 1. Now, we would like to go ahead and expand it term by term. So, first let us take the first term in the approximation in the expression. The first term in the expression let us say is expected value of B times R Hermitian, B times R Hermitian. Now, please write down or substitute the value for R. This would be expected value of B times RB plus eta Hermitian, and this would be equal to, if you were to expand it, it would be equal to B times B Hermitian times R Hermitian. But we know from the property of the correlation matrix that R satisfies the property that R is equal to R Hermitian. So, we could equivalently write this as, instead of R Hermitian, you could write it as R. Now, the second term in this expression, so this would be the first term, the second term would be expected value of B times eta Hermitian. Now, notice that one of these components is the input vector, which is a binary vector equally probable plus or minus 1s, and the other one is the noise vector, which again has got 0 mean. So, the second term can be ignored because the expected value will go to 0. What we have is the first term only. So, even in the first term, R is a constant matrix. So, what we are interested in is in B Hermitian, and when we look at the expressions for B and B Hermitian, if we were to write it down, this is B1, B2 up to Bk, the number of users, times B1, B2 up to Bk. Notice that the diagonal terms will give you B1 squared, B2 squared all the way up to Bk squared. So, when you take the expected value of plus 1 squared is equal to 1, minus 1 squared is equal to 1. So, you get 1s along the diagonal, but keep in mind that the vector B itself actually incorporates the energies of the transmitted signals. So, it would actually be correct to call it as root E1 times B1 root E2 times B2 all the way to root Ek times Bk. So, this would be the correct expression. So, what we should do is introduce the values root E1, root E2, root Ek as the, and here again we would introduce the root E1, root E2 and root Ek. So, that would be BB Hermitian. So, when we look at the expected value, this basically becomes a diagonal matrix where it becomes diagonal value E1, E2, Ek. Off diagonal terms are a product of B1 and Bi and Bj, both are independent and each of them is equal is 0 mean. So, therefore, the off diagonal terms become 0. So, this becomes the BB Hermitian. So, so this is expected value of B Hermitian is given in this form. So, this equation now becomes expected value of B times R Hermitian is nothing but, if you were to call this matrix as D, where D is a diagonal matrix whose entries are E1 through Ek, then this becomes equal to D times R. So, the first expression term in the expression is d times r. So, this is equation 2. So, going back to the expression, we are trying to write down a expression for based on the principle of orthogonality. The first term was b times r Hermitian, the second term was a times r Hermitian. We are trying to get expressions for both. We have now completed getting the expression for b times r Hermitian in terms of d times r. Let us move on to the next term in our expression. The next term in the expression is expected value of a times r Hermitian, Hermitian. Okay. So, this would be expected value of a times, write down the expressions for r. The expressions for r is r times b plus eta. The second term would be r times b plus eta Hermitian. So, this again if you were to expand this product, we would get 4 terms, and what we would like to do is quickly look at what those 4 terms are. So, the first term would be expected value of a times r times b Hermitian times r. You should get r Hermitian, but that would be same as r. That would be the first term. The second term will be, there will be 2 terms which contain expressions for b or b hat. Now, expected value of this would be 0 because the individual components are 0 mean, and then the last term will be expression with the 2 noise terms, which will be a times eta Hermitian. Okay. So, these are the expressions that we have. So, if you were to take the value of expression expectation inside, we can show that this becomes a times r times, remember expected value of b Hermitian, we got it to be equal to d, and then we got to write down this as r Hermitian. Now, if you were to write down the expression for expected value of eta hat, if you were to if you write down the expressions for that, we have already shown that this is equal to expected value of eta hat, we have shown is equal to n naught times the n naught is the noise variance times the correlation matrix, where r represents the correlation between the different spreading sequences. Now, if you were to write this down, this would become plus a times n naught times r, a times n naught plus, and this is expected value of a times r Hermitian. This is, take this down as equation 3. So, equation 1 gave us the expression to, for based on the principle of orthogonality. Equation 2 gave us an expression for the first term. Equation 3 gives us an expression for the second term. So, if you now were to go back and substitute the values d, so then what we would get is equation 1 can be equivalently written as d times r from equation 2 minus a times r d r Hermitian minus a times n naught times r from equation 3, and this has to be equal to 0. We are basically substituting in equation 1, substituting in equation 1 from 2 and 3. That is our basic operation, which is what gives us this expression. And we also know that r Hermitian is equal to r, so we can simplify this. So, now we do the following expression. So, think of the following form, where we write this as d times r minus A times R times D times R, because R Hermitian is equal to R, minus A times N naught. I am going to write D inverse D, basically that would be give me the identity matrix. I am basically substituting D inverse D into this in between N naught and R multiplied by R equal to 0. Now you may wonder, is D inverse, does it exist? Yes, it exists, because D is a diagonal matrix with the energies E1, E2. So it is basically a diagonal matrix with non-zero entries. So therefore the inverse exists. So there is no issue with writing D inverse times D. So now notice that I can factor out D times R from this expression. So then it becomes I minus A times R minus A times N naught D inverse times D times R equal to 0. Now from this equation we know that D is non-zero, R is non-zero, R is the correlation matrix between the spreading waveforms. So D and R cannot be 0. So from the observations, this term must be equal to 0, which basically tells us that I minus, if you factor out the A matrix, R minus N naught D inverse, R plus N naught D inverse, sorry, must be equal to 0, which also tells us that A has to be equal to, basically if you take one term to the other side, A has to be equal to R plus N naught D inverse D inverse. In other words, A times R plus N naught D inverse has to be equal to identity matrix. So therefore A has to be the inverse of that matrix. So this is a very, very important result. Now we started off by saying that the MMSE solution will give us an estimate of the transmitted vector, where B is equal to B hat is equal to A times R, and the steps that we were doing is actually to find out the expression for the matrix A, which will give us the best possible solution B hat. And through using the principle of orthogonality, writing down expressions for each of the terms given by the principle of orthogonality, we have been able to derive the following expression. Now what we would like to do is understand this expression a little bit more. So the MMSE receiver that we have derived so far has the following properties. We said that B hat will be equal to A times R, and we wanted to minimize B minus B hat magnitude squared expected value, and this resulted in us obtaining the matrix A in the following manner, which is R, the correlation between the spreading waveforms, plus N naught, that is the noise variance of each of the antennas, multiplied by D inverse and the whole inverse. Now what would be very helpful for us is to look at two special cases. The first special case that we would like to look at is, so this is case 1, special case, and we would like to look at the case where the noise variance is small. Okay. So in other words, the additive noise from each of the antennas, the thermal noise, is small compared to the other forms of interference, the multi-user interference. So N naught is small. So if N naught is small compared to the in the expression, then the expression here can be approximated as R plus N naught D, because N naught is small, we ignore N naught D, D inverse. So this becomes R inverse. Notice that what this is telling us is the MMSE solution is the same as, in this particular case, MMSE same as the decorrelation receiver, same as the decorrelation or decorrelating receiver. And it is a very interesting result, because what did we say was the drawback of the decorrelating receiver? The decorrelating receiver, we said, may result in a noise enhancement. Now, if the noise enhancement is the noise itself is small or negligible to begin with, then we can ignore the effect of noise enhancement and say that the decorrelating receiver is the best possible solution, and the MMSE receiver more or less confirms that that is the best way to do that. Now, of course, we take the other extreme, where the special case number 2 says that N naught is large. So, this is the case where the decorrelating receiver will not do a good job, because it will end up further magnifying the noise. Now, notice that if you were to have this expression, N naught becomes large. So, therefore, we between R and N naught D inverse, the second term dominates. So, under this condition, we find that the expression for A can be written in the following manner. It is given by E1 by N naught, E2 by N naught after D inverse inverse. So, basically notice that there are 2 inverses given, and finally it is Ek by N naught, Ek by N naught. Notice what is this telling us? Remember, our best estimate for the transmitted vector is B equal to A times R. So, what the MMSE receiver is telling us is that when N naught is substantial, when N naught is a significant noise component is present, then the best that we can do is make a decision directly on the output of the correlators, because A is nothing but a diagonal scaling matrix. It says B1 based on the output of R1, B2 based on the output of R2, because any attempt to do the suppression of the multi-user interference ends up further degrading the noise and not giving us any additional benefit. So, basically this is both the special cases, one where N naught is small and the one where N naught is large. Both of them give us a good explanation of why the MMSE receiver works in both these environments. So, to summarize, the MMSE receiver is one where we write down the expression that you want the output or the decision to be a linear combination of the output of the correlators, and the expression for the matrix A is given by the following expression, and this is the MMSE receiver for multi-user detection. And the decision statistic itself is given by A times R, where R is the output of the K correlators, So, we get received correlators, and we get a set of received signal, pass it through each of the K correlators, match filter to each of the K spreading waveforms. You get the vectors R1 through Rk, uppercase K. You are able to pre-compute the matrix A, do A times R, and then do the decision based on that. Okay. So, to go back to the figure that we drew. So, CDMA multi-user detection, it is a very vast problem, widely studied. What we have tried to do is to give a flavor for what are some of the aspects. The first one is the optimal solution requires you to do an exhaustive search of all combinations of the transmitted vector. The suboptimal solution, the one that we saw first, was a decorrelating receiver. A decorrelating receiver is one that computes the correlation matrix, inverse of the correlation matrix, and then makes a decision based on that. So, this would be R inverse times R is the decision made by a decorrelating receiver. On the other hand, the MMSE receiver says it would use the matrix R. It also uses an estimate of the noise in the system. Noise times the D inverse, D representing a diagonal element, a diagonal matrix with the energies of the different transmitted signals inverse. So, notice that when n naught is large, n naught is small, it converges to the decorrelating receiver, and when n naught is large gives you a solution which is different from the decorrelating receiver and which turns out to be the best in. So, anything in between where you do it is somewhere which is neither the very low noise or the very high noise, anything in between, we find that the MMSE receiver is a good solution for us, and we get the decision statistic B hat to be equal to A times R, where A is given by this matrix. Okay. So, that summarizes for us the CDMA multi-user detection, and also concludes our discussion on the chapter of CDMA. I hope you will have a chance to read the corresponding text, the material both from each of the books. The coverage that is presented in each of the books adds a unique flavor. Definitely I would encourage you to read the corresponding chapters in Rappaport's book, also in Haken's book, Molish, and in Goldsmith. Each of those adds a different perspective, and of course the multi-user detection part is very nicely covered in ProACUS. So, general CDMA, the concepts of CDMA from each of these books, and the multi-user detection, very specifically the decorrelating receiver, the MMSE solution, a good reference would be ProACUS digital communication. So, I hope you will be able to get a good understanding and a confidence of that, because CDMA is the backbone of our 3G systems and our 3.5G systems. So, whether we are talking about CDMA 2000 or we are talking about wideband CDMA, or any of the enhancements such as HSPA, these are all based on our understanding of CDMA and how we achieve capacity, how does the base station do multi-user detection, and all of the benefits and the complexities of a CDMA system. So, that would be a good summary of that. Now, having completed the discussion on the multi-user detection, we would now like to move into the next big aspect of the wireless systems, where we have the benefit of multiple antennas both at the transmitter and receiver. Now, we find that in the fourth generation and in the fifth generation, as we presented in the introduction, the use of multiple antennas has become a very significant and a very prominent feature, and that is something that we want to gain a very good understanding of from the point of view of the course. So, with that in mind, we would now like to look at the formulation of the multiple antenna environment. So, multiple antennas at the transmitter and receiver, the multiple antennas and transmitter receiver, which is being characterized in terms of there are NT transmit antennas. So, NT antennas at the transmitter, and correspondingly we have NR antennas at the receiver. So, NR receiver antennas. Now, there is no assumption being made as to which is smaller or larger. NT can be greater than NR, can be less than NR, or can be equal to NR. All three combinations are possible, and we will mention the various scenarios that are likely to happen. So, in the most general framework, what we find is that we can look at the transmit side as a set of NT transmitters, which is transmitting to a set of NR receive antennas. Now, for a moment, take the case where you just have one receive antenna. If you have only one receive antenna, what you will find is the transmitted signal from antenna 1 which goes on the first branch. Let us call this gain as H11. So, I would like to call this this particular gain as H11. So, that is the signal gain from at receive antenna 1 from transmit antenna 1. Similarly, if you look at the so the receive antenna 1 from transmit antenna 2, call it as H12 and H1 comma NT. So, basically there are three, keep in mind we are looking at the case where there is only one receive antenna. So, we get three different signals that are received by antenna 1, each of them having a complex gain denoted by H11, H12, H1 comma NT. Now, if you were to write down the from the other side, from let us consider only one transmit antenna and NR receive antennas. So, the first antenna transmits, it is picked up by antenna 1, that would be H11. Now, the signal picked up by the antenna NR would be H times NR comma 1. So, that would be the receiver. So, like that each of those receive antennas would be picking up the signal from antenna 1. So, this is a important framework of characterization. So, when we have the general case of NT antennas at the transmitter, NR antennas at the receiver, then we can write the expression for the MIMO system in the following way. So, if you were to write down the output of at the receive antennas, Y1 of N, which is the first receive antenna, this would be H11 of N times X of N, X1 of N, the first transmit signal from the first transmit antenna. Then H12 from the H12 of N basically shows that these are all time varying quantities. The channel can be a time varying quantity. So, H12 of N times X2 of N plus dot 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 H1 comma NT of N times X of NT of N. Notice that this would be the expression for the signal received by antenna 1, and as in all of the communication systems, each antenna adds the presence of thermal noise is reflected by a noise component which is given by N1 of N. So, if you were to capture this in matrix form, it would be Y1 of N, Y2 of N dot 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 YNR of N. Notice the index is NR because there are NR receive antennas. So, this would be a NR cross 1 vector. The vector in the middle, the channel matrix, would be H11 of N, H12 of N all the way to H1 comma NT of N. The last term will be HNR comma 1 of N, HNR comma 2 of N dot dot dot, last term will be HNR comma NT of N, and this multiplied by the signal transmitted by each of the transmit antennas, that would be X1 of N, X2 of N all the way to XNT of N, and each of the receive antennas has its noise component represented by N1 of N, N2 of N all the way to NR of N. Let us quickly write down the dimensionalities of each of the vectors. The transfer matrix is NR cross NT. The transmit vector has got NT components. So, this is NT cross 1, and the noise source is NR cross 1. Notice that it will be dimensionally consistent, and we can write it in the following form: y is equal to h times x plus n in compact form. So, this is the problem or the formulation of a MIMO system. There are NT transmit antennas, each of them transmitting a signal, and NR receive antennas picking up the transmissions from each of the NT transmitters, and of course, the noise terms being added in each of the receive antennas. So, in a compact form we can write it as y is equal to hx plus n. So, the MIMO problem statement is that we are given the observation y, given the vector y. We assume that the channel matrix is known H. The task before us is to estimate x. Okay. So, that is the MIMO problem statement, and that is something that we will pick up in the next lecture and build on, so that we can get a good understanding of how MIMO systems work and what are the advantages and the benefits of using MIMO in a wireless system and very specifically in a cellular type environment. Thank you very much.